So welcome everyone to the first Quantum Energy Initiative seminar. So just as a reminder, the Quantum Energy Initiative is a consortium of international researchers along with founded by Alexia Auffèves, Robert Whitney, Olivier Srati, and Janine Sletterhauser. We are 10 people in the board, and we have over 100 members. And our goal is to promote a different view on quantum technologies, which is not based necessarily on making high efficiency or high rate devices, but to estimate their energy consumption, maybe find some advantage on that, and define metrics along there. I'm very proud to introduce Marco, who was a student of Alexia for his PhD, who's now working in Warsaw, and who did, in my opinion, one of the most important and pioneering work on the topic that he will explain to us right now. Marco, the floor is yours.
Thank you. Thank you for the invitation and to present this. So yeah, what I will present today is this work that is on archive now. That has been done. So it's about indeed a designing methodology to minimize the energy consumption for quantum computers, and it's a work that has been done in collaboration with everyone here. So just quickly, so Jinhao was a postdoctoral, the PhD student of Wei Kun. He specialized in fault tolerance, and Wei Kun is also specialized in fault tolerance. She works at the CQT in Singapore. Yvan Tonard is a specialist in classical electronics, working at the QEI in Grenoble. And Robert Whitney and Alexia Auffèves are my PhD supervisor in Grenoble, specialized in quantum thermodynamics, and Alexia works in the CQT in Singapore as well. So, and yeah, so I'm currently working in Warsaw. So what's to understand the question of minimizing the energy consumption of quantum computer, there is a strong connection with the computational advantage, but the problems are different. So first, I would like to recall why we want to build quantum computer. So we want to build quantum computer because we know that there are some problems when we increase the complexity of the problem we want to solve. The number of operations required by a classical computer will increase exponentially with the size of the problem. While on a quantum computer, the number of operations will only grow polynomially. So this is what we call an exponential speedup. And basically, we know that if the problem is large enough, because there are such a big difference in number of operations, it's obvious that at some point, for a problem large enough, the quantum computer will save time. So a typical example of exponential speedup is Shor's factoring algorithm, where the problem size is not the number you want to factor, but the logarithm of the number of bits it's written if. So it's the technical detail, but basically you have this kind of exponential speedup. So the question of energy advantage, first, there are things that are obvious from that. So it's clear that if the problem that we want to solve is large enough, the quantum computer will bring an energy advantage, simply because the difference in number of operations, you can put it as large as you want. So if the problem is large enough, it's clear. What is less clear is when the transition occurs between a moment where a quantum computer might not save energy and the moment where it will save energy. So when this transition occurs. And what we would like is, so first, why is this question important? There are two reasons for that. So the first one is that if you want to make large-scale quantum computer, we need to make sure that we can build them. And if they consume too much energy, it might be that it's not possible for purely feasibility reason. If you imagine a quantum computer that spans more than a nuclear reactor, to give an example, you will likely not build it because no one will be ready to make that. So this is first a question of pure feasibility. Then there is another thing that is interesting behind this question. It's could we build a small quantum computer which will not necessarily give us a computational advantage, let's say not a significant computational advantage. They will solve a problem in a time comparable to a classical computer, but they will do it by saving, I don't know, orders of magnitude of energy. And this could be another motivation for the field. And what I find interesting in this question is also that it might be easier to build such kind of quantum computer. So why am I saying this? It's because if you are not looking for the computational advantage, you do not necessarily need to make this huge large-scale quantum computer. You could have a quantum computer of intermediate size, much more doable. Of course, people have to optimize things so that it's energy efficient, but it might be easier to build. So that's the two motivations behind this question. And so we need to find where this transition occurs to put it the earliest possible. So, and we need a methodology for that. So this is what we propose here. So what we propose is a holistic methodology. So what holistic means is that we can apply it to a complete model of quantum computer and optimize altogether the computer. It means that we see the full computer as a physical system where you have error correction, algorithm, the physics of the qubit, the enabling technology, and we have one model of the computer and we optimize it such that it minimizes the resource, which in this talk will be the energy or the power consumed by the computer, but it could be other things. Just that we think that this is a good focus to maximize the scalability. So then what I will discuss is that we will apply this methodology. So in an idealistic model of a full stack quantum computer, so it means complete, where we try to be exhaustive. And we will minimize its energy and power consumption to crack RSA, so the main encryption protocol, that you can crack with Shor's algorithm, and we will see which kind of order of magnitude to expect. So I will repeat this along the talk, but what is very important to understand is that what is shown here is not an accurate estimation of how much power or energy it will cost. This is too complicated to do now. It's rather a proof of concept that we can use interesting methodology to optimize their consumption and that it can be very useful. So the thing is that we will have very idealistic assumption for the quality of the qubits. And the model is based on a specific error correction code, which is STEAM concatenated. So there are reasons why I will explain this after. But I really want to say this now. But even with that, so you can see this as a toy model of a complete quantum computer, full stack, and it can already give interesting idea of what will cost, what is likely to cost, and to get intuition of the order of magnitude we could potentially expect still. So the methodology that we introduced is called MNR for metric noise resource. So its principle is very simple, but I introduce it now. So basically, you have, as I said, this metric, this noise, and the resource, and in the middle, you have some control parameters. So the metric, it is just one number that tells you how accurate your computation is. You can think of it as the probability that your algorithm succeeds. So you would like a high metric. It could be the fidelity of the output set. You could consider other things, but you need one number that tells us how good the computation is in terms of reliability. There is then the noise. So the noise is a description of the physical process that occur at the level of the qubit. So an equation of motion that describes how noisy your gate are. And you have a resource. So that is the thing you want to minimize. In our context, it would be the energy or the power consumption. And in the middle, you have control parameters. So these control parameters, they characterize the architecture of your quantum computer. It can be the temperature of the qubit, the number of physical qubit per logical qubit, the temperature at which you generate signal, etc., etc. And basically what happens is that when you will modify the architecture of your quantum computer, it will modify the behavior of each of these things. If you change the temperature, you modify the energy it costs to run the computation, because as you might know, it's hard to remove heat at low temperature, think in terms of thermal efficiency. So if we change the temperature of the qubit, the consumption will be different. But we will also modify the noise when we do that. We want to put the qubit cold because we don't want them to be too noisy. And because of that, we will change the success of the computation. Those control parameters will modify these boxes. And what you can simply do, so I take a simple example with the qubit temperature. You ask by tuning this qubit temperature, so you modify the amount of energy, how the noise acts, and then the quality of your computation. So what you can ask is the most basic question you can ask: what is the minimum energy or power I need under the constraint that my algorithm succeed with, I don't know, 90% of accuracy? And by doing this, so you will, for instance, be able to optimize the qubit temperature such that you reach this success while spending the least amount of energy to do it. And so this is very simple. It's just a minimization of the constraint. But what is interesting is that you can really use it on a full model of quantum computer and optimize everything for the physics of the qubit to the algorithm, the error correction, and so on. So we will see example after. So I will start with the very simple pedagogic example. And on the bottom right, you will see the step in the modeling, and it will give you an idea of the level of detail we use in the full stack model introduced after. So here, we would like to do a single qubit gate on superconducting qubits. So a superconducting qubit, they must be inside some cryogenic units. And to drive them, what you do is you send signal into microwave cable. So the signal go down and interact with your qubit. And when they interact with your qubit, you do your gate, your Hadamard, or whatever you want to do. The thing is that those signal, so let's say the qubit is cold at some cold temperature. The signals, they are not generated at the temperature of the qubit. So if the device that generates your signal is at room temperature, the signal will be very polluted by the noise. And to avoid that, experimentalists typically put attenuator, which are big resistance that basically dissipates, let's say 99% of the signal that arrives. So it dissipates a lot of heat, but it isolates the qubit from the noise that is at room temperature. If you want to you dissipate useful signal, but also noise. And this way you can reach a high signal over noise ratio if you put a good amount of attenuation. And then the signal interacts with your qubit and you do your gate, the little fraction that passes the attenuator. So in this example, we can specify the control parameter of the optimization. It will be the level of attenuation input and the temperature of the qubit. And we want to minimize, let's say, the power consumption to do this gate. So we take a Carnot efficiency and we multiply by the heat to evacuate. And that is very, very simple toy model of a single qubit gate for the power part. But as I said before, this is only one part of the problem. What are the optimal control parameters I should put? Then we enter in the noise model. So here we specify the noise model we use to make the gate. So basically what we have is what we have in this model, and it's also relatively general, at least in the philosophy. You have an Hamiltonian, so a perfect dynamics, and then you have some noise that will corrupt this dynamic. So in this simple model, and that's the same noise model we will use after, we will assume that we only have this kind of noise model. So basically, the quality of the gate will only be bad because of two effects: spontaneous emission and thermal relaxation. And the qubit will absorb noisy photon and can relax or be excited because of that. So here, what you would like is this red part to be equal to 0, and then you will do a perfect gate. But it's not possible. And so, as I said, there is a part that is due to the thermal photon. You have noise in your signal because of temperature, because of the temperature at which it has been generated, because your qubit is not exactly at 0 Kelvin. And so it contributes to the noise. But what you can realize is that even if this n noise is equal to 0, you will not completely kill the noise, because you will have this part that will remain, because here you have gamma times 1 plus n. So even if n is equal to 0, you still have this. And the remaining term is the spontaneous emission rate. So it's the quantity. Its inverse gives you the lifetime of the qubit if it was in an ideal world at 0 Kelvin, perfectly isolated. It will still be noisy. That's fundamental limitation, spontaneous emission, and it will quantify the quality of our qubit. So later, when I will talk about the quality of the qubit, it will be the inverse of this coefficient gamma. So this is the noise model, and now we need to relate it to the control parameter. So here, the number of thermal photons is related to the attenuation and temperature of the qubit through this expression. So I won't comment in detail, but it's just to say, so this is the Bose-Einstein population. So you have a first term here that characterizes the temperature of the qubit. So if the temperature of the qubit is exactly 0, this term vanishes. And you have an additional contribution, which is due to the fact that the signal are generated at room temperature. So you need to attenuate them to remove their noise. And this is how this part of the noise is killed. So you see that both the attenuation and temperature play a role on the quality of the qubit. And finally, we need to specify the metric and to express it as a function of the control parameter. So I won't go into detail. We want to do a single qubit gate. We look at its worst case fidelity, and we have a simple expression from the noise model. So this is not very complicated to do. And then we're ready to do the minimization on the constraints. And just to say the general trend that will always be observed, it's that or the following. So here, that's the power consumption of your gate as a function of the attenuation you put on your line and the temperature of the qubit. So the lighter this graph is, the more power your gate consumes. And what you realize is that naturally, if you attenuate a lot, and if you put your qubit at very cold temperature, your gate is very costly. And that's the other opposite behavior if you're on the upper left part, which means high temperature and low attenuation. But if you want a high quality for your gates, you should also attenuate a lot and put your qubit at low temperature. So it is not possible to say at the same time, I want my gate to be cheap in terms of power, and I want it to be noiseless. There is a trade-off. You have to pay something. And basically what you can say, then you do the minimization of the constraint, and you say, I want my gate to reach, let's say, this fidelity, 9995 here, 0.9995. It gives you a constraint on the parameter you should put to drive your gate. And then you ask, what is the minimum power for this quality of my gate? And then it gives you that point, which gives you at the same time the optimal temperature for the qubit and the optimal attenuation. And you can play that role with different quality for your gate. So what is very important to understand is that it is impossible to ask the best gate possible because the power will diverge. Why? Your qubit should be exactly at 0 Kelvin. The Carnot efficiency diverge and there is an infinite cost. So you should always fix what you consider a reasonable target for your need, and then you do the minimization of the constraint. Okay, so as you see, this is quite simple. But what is interesting is to apply it in a complete model of quantum computer to optimize its full architecture. So this is what we did. So this is the model of quantum computer we considered. Again, it's a toy model. This has to be improved. It's based on idealistic parameter, but in principle, there is all the elements you need for a fault-tolerant quantum computation. So everything you see here inside this gray square is inside a cryogenic unit. There are also elements outside. I won't comment too much on them. Let's focus on what there is inside here. And each gray plate you see is a cryogenic stage. So here it's a given temperature, another temperature, and yeah. So the first stage we see is the stage where the signal will be generated. It has a given temperature, and we will optimize that stage. So when the signal are generated, they go down through the coaxial cable here. You recognize all the attenuator. I explained the reason why they are here, to mitigate the thermal noise. Then you have your qubit, you do your gates. And when you want to read the qubit state, you have to send pulses to read the qubit state. And when they go up, they are amplified, digitized, and so on. So this is that's the reading line on the left and the driving on the right, and the driving on the left. So we have these intermediate stages here. So where we put an attenuation and and there are the given temperature, we will also optimize this thing. So we optimize this temperature. The attenuation and temperature are all these stages. So that's the amplification stage. They are modeled, but we do not optimize them. And here there is a stage where the qubits are, and we will optimize the attenuation we put and the temperature of the qubit. But as I said, we will do fault-tolerant quantum computing. So we also have quantum error correction that is here. And we use concatenated code. So before explaining why we took that code, I would like to explain in very simple terms how error correction works. So when you want to do error correction, you have one parameter. So in that case, I call it K, the concatenation, it's the concatenation level. We work with concatenated code, such that when you increase this parameter, you add physical qubit per logical qubit. So this is this term here. Here, that's the number of logical qubit, and here, that's the number of physical per logical qubit we will have. So why do you want to increase K? Because the computer gets bigger, and so it will likely cost more energy. The reason is that when you add those components, you're able now to detect and then correct errors. And how does that work? So here, you can define the probability of error of a logical gate. So it means a gate protected by quantum error correction. And it reads like this. So where here you have a constant called the threshold. And here, this is the probability of error of a gate if you did not do error correction, so a physical gate. What you can see here is that if this physical error is below the threshold, you have a term that is less than 1 here. So when you increase K, this term, you can put it as close to 0 as you like at the cost of increasing K. So it means that you can make your logical gate as reliable as you want if the physical error was below the threshold at the cost of adding physical qubit in the computer and also adding physical gates. So these things are inside the model. They will be used. So first, of course, the number of physical qubits, it will play a role here. It will scale all this part of the computer and also actually the part that generates signals. But also when we do error correction, we can decompose a logical algorithm. We can look at how it's compiled on the physical level. So when we have this concatenated construction, and we can say, let's say I want to do an error-corrected logical CNOT, we can split it in which operation undone on which qubit at which time, and from that we will be able to estimate the signal per unit time that will reach the qubits, which will scale the heat dissipated in the attenuator, for instance. So we can access all this. Okay, so that's the error correction code we use, and that's the other parameter we will optimize, the concatenation level, so which will give us the number of physical qubit per logical qubit. So now I quickly explain why we took that code, because you might know that to scale up, especially superconducting qubits, we would like to use more like surface code rather than concatenated code. So there are two reasons. The first one is that it's complicated to make a complete model of quantum computer, and we could not face all the problem at once. So we choose this class of code because we can do analytic calculation with them. We can estimate nicely each physical operation are occurring at each time, etc. And so that's the first reason. The other reason is that if we use surface code, so it's possible to do the same kind of thing, but there is one thing, which is surface code requires some classical computation to decode the syndrome from error correction. So this is also the case with concatenated code, but basically when you have an error occurring on your physical qubits, you need to fix it. And to do it, you have a classical algorithm that reads the state of the qubit and that say, this qubit had this error, so I need to correct by doing this. With concatenated code, this is very cheap, this decoding. It will be below the order of magnitude of other important thing in our model. So we could neglect it, it was fine. With surface code, it might be a significant cost, and that's an open question to know exactly how much it costs. So we preferred also to have a complete model, maybe based on idealistic assumption, but at least we have the full model of quantum computer. So that's the other reason. So at this point, all the parameters are specified. So all the temperature of this stage here, the attenuation we put also, the concatenation level, and that's the first part. Control parameter and resource has been specified. Then we model the noise. It's the same noise model as before, so I won't comment too much. And then the metric. So how do we say that our algorithm succeeds? What do we use to quantify this? So when we do error correction, we have this probability of error per logical gate. And we can use that to say, what is the probability that my algorithm succeed in the following sense? We have a given number of logical gates. We compute the probability that no gate failed along the computation, meaning that everything was reliable. And so it gives this equation. And basically we impose, so it depends, of course, on the temperature of the qubit, the signal generation, the concatenation level, the attenuation, because they play a role in the physical error rate and also in the logical error rate, because when you modify the physical error rate, you also modify the logical error rate because they are related here. And then we ask the algorithm to succeed the typical value 2/3 of the time. So for Shor's algorithm, this is a typical value that is used. There is nothing fundamental about this 2/3. It's just we want something relatively close to 1. And because with Shor's algorithm, we can easily check if it's wrong, because it's easy when it gives you, when it has decomposed a number in prime factor, you can easily check if this is the good prime factor. So then you do not need to ask for a super high quality, because you just run it a few other times and then you have the answer. Because if you have this probability, you just need to run it maybe 2 or 3 times more to have the good answer if it's wrong, to a high accuracy. So yeah, that's it for this. And then then we can apply this. So we are almost ready to see the plots, but basically. Yeah, so as I said before, this is a toy model. There are idealistic assumptions, but it can still provide Roth intuition about the order of magnitude to expect. So what are the main assumptions? this is the thing that, in my opinion, are the most important to know about the results. The main optimistic assumption is the quality of the qubit we make. So we assume that their lifetime, so the inverse of the spontaneous emission rate. So if they were perfectly thermalized at 0 Kelvin, the lifetime will be 50 milliseconds. So to put this in perspective, if you had about 5 milliseconds, it's, let's say, the state-of-the-art lifetime for one Transman qubit that you do not manipulate in a perfectly idealistic environment. So it's one order of magnitude bigger than that. But if you consider the gates, I don't know, like IBM or Google, if I remember correctly, this is about 2 or 3 order of magnitude better if you try to make a quicker back-envelope analogy with that. So it's very good qubit. Of course, we don't have qubits ready today to do error correction, but we need to be even more demanding because we use thin code, which has a lower threshold than surface code. Then there is another assumption that is optimistic, but not that much optimistic. It's clearly not the same thing. So as you saw, we have electronics that is here to drive the qubit to generate signals. And here we consider that it consumes 1 milliwatt per qubit, which is a bit more than 1 order of magnitude improvement to the state-of-the-art CMOS electronics. But when we discuss with electronics engineers, they consider that it's clearly a reasonable thing to take because there are many improvements that can be done. I won't comment it too much, but basically this is not. I mean, this is a plausible, much more plausible assumption for the quality of the electronics. And finally, the efficiency of the cryogenics we took is Carnot. So it might look as a crazy assumption to make, but actually it's not. Because the Large Hadron, to give an example, the Large Hadron Collider, when they do particle physics in Geneva, it works at a fraction of Carnot efficiency. It is like 20 or 30% of Carnot. So it's a much better efficiency than what experimentalists typically have in their cryogenic system on small scale experiment. But just because this is not a cryogenic that has been optimized. If you want to reach the large scale, for me, we will need to go toward Carnot. So this is what we took. And I will show the results as the power consumption as a function of 2 parameters for the algorithm we implement, the number of logical qubits it requires, and the time step, the depth of the algorithm, which means the sequence, how many sequence of operation you need to do. And this is the kind of result we can get when we perform the optimization. So in the x-axis, you have the number of logical qubits, and in the y-axis, you have the number of time steps for your algorithm. So here, for instance, for RSA 2000, it would cost 7 megawatts for a few hours with our model, and we can look at other values. And let me comment a little bit this curve. So what you can see on this curve is that there are brutal transitions. So here, here, here. So these moments are when we need to add physical qubit per logical qubit. So that's when the script tells us, now you should add error correction. Otherwise, your algorithm will either be wrong, either you will not be energy efficient. So it's this thing that happens. Another thing you can realize is that the longer the computation is, the more power it costs. So I will come back to that point, but because at first view, we might think that I run my quantum compute, if I want to be energy efficient, if I run it for 1 or 10 hours, the power consumed will be the same. It's just the energy that will be multiplied. But actually, it's not true. The power will grow with the duration of the computation. I will explain this a bit more after. So as I said, this is not an estimation, but an optimization. So each point that you see for each algorithm implemented is the result of an optimization of the computer architecture. So let me give intuition about what is happening. And this is the key points in the approach. If you understand that, you understand everything, basically. So on the right, you see the temperature of the qubit as a function of the algorithm we want to implement. So let's say we start on that point here. So we just added physical qubit per logical qubit because we are just after this brutal transition here. So what the script tells us is that, okay, now you just did a lot of error correction. You just added physical qubit per logical qubit. So if you want your computation to be energy efficient, because you do a lot of error correction, put your qubit at a high temperature. You will save power by doing this. It's okay. Your qubit will be more noisy, but it's okay. You do a lot of error correction. And then you increase the duration of your algorithm. And so you need to preserve quantum information for a longer and longer time. So now you have to pay the bill. You have to inject more power to be able to guarantee a success. So then the script tells you, okay, cool down your qubit, cool down your qubit, cool down your qubits, until you reach that point. The qubit are at 4 millikelvin, and then the script tells us, if you want to go further in such a manner that your algorithm succeeds, but spend the least amount of power, there is no choice. You should add physical qubit or logical qubit now. You add them, and then the qubit temperature increases again, because now you just did more error correction, so you can be more relaxed on the temperature of the qubit. So this effect, quantitatively, what you see here is, of course, specific to this model, but qualitatively, this is something you will have for any kind of energy-efficient quantum computer. It's really a multidisciplinary effect that comes from a holistic modeling. You cannot understand it if you reason in isolated manner. Basically, it's a combination of the physics of the qubits. Why are these temperatures quite low? I mean, we never see 10 Kelvin, for instance. It's because the noise model of the superconducting qubits are how they are, and you will be higher than the threshold, for instance, if the temperature was too high. It's related to the way we implement the algorithm. When you see that when I increase the duration of the algorithm, the temperature decreases accordingly. It's related to the error correction code we are using. This transition here, they are occurring because we use this code. And actually, so I will comment also this after. I think that with a better code that is less resource demanding, what you will see here will be much more smooth. Here, it's really, when we do concatenated codes, we brutally add a lot of physical qubit or logical qubit. If you use another code, the thing will very much smoother, and you probably won't see even any transition because all the temperature will smoothly adapt. And finally, of course, it's an effect induced by cryogenic engineering. Why the script would like to put the qubit at the highest temperature it can after transition, because we want to minimize the kernel, the power consumption and there is the kernel efficiency, there is the electronics, the heat dissipated. So there's all the enabling technology, if you want, behind that. Yeah, so now I would like to make a kind of general discussion of what does it mean to do an energy efficient computation. So basically, the power of a quantum computer, you can see that if it's energy efficient, it should grow the longer the algorithm is. Because the longer the algorithm is, the more you have to pay to maintain reliable quantum information. So you will have a growth of the power with the duration of the algorithm. Let me give you an example. Let's assume that the power to run the algorithm was constant. What would that mean? Basically, it will mean that either the output of your algorithm is wrong, either that the computer spends too much power at some point. Because here, for instance, yes, it will be constant, but we will spend more power than what the optimization will say. And then when we increase the duration, so we need to spend more power to preserve information, then you will have a crossing here. And here it will get higher than this constant power. And basically all this area in blue would mean that the algorithm will give you a wrong answer if you stayed with this flat here. So an energy efficient quantum computer, you should see that its power increases the longer the algorithm you want to do is. And said differently, if we think in terms of energy, it means that the energy increases more quickly than linearly with the duration of the algorithm. So to say it differently, a quantum computer that is energy efficient and that succeeds, if you multiply by 10 the duration of the algorithm for all other parameters fixed, of course, it will consume more than 10 times the energy. Otherwise, it means either your computer is not energy efficient, either it does not give you a trustable answer. So I think that an energy efficient quantum computer, the growth of how the energy or the power grows should grow very smoothly with the duration. So why do I mean that? If you increase just a little bit the duration of your algorithm, you should just add the epsilon extra power consumption or energy that allows you to reach that success. So if you have big jumps, it means that the design is not so optimal. And actually, if you remember the plot I showed, we had big jump. So we are optimizing, but it shows that it is still not energy efficient because we have this moment, or brutally, we need to add error correction. And if we had a smarter error correction code, it will do the thing much more smoothly. So now that we understand that, we can also compare the energy efficiency of quantum and classical computer. and see if we can reach an early energy advantage. How to make a fair comparison. So I will first say how not to do it because it's interactive. You will see it's always the same kind of things that I say in different manner. So how not to do it? You could think about each operation has an energy, and you multiply this energy by the number of operations. For instance, in classical computer, a floating point operation costs this amount of energy. Multiply this by the total number of operations you have in the algorithm, and it will give you the energy consumed by this algorithm. If you want to do it on a quantum computer, because it is so sensitive to the noise, you will be wrong in the sense that either your algorithm will not be energy efficient, either it will be wrong. Let me give you a simple example. Imagine you want to do a single qubit gate. You have 1 qubit, you just want to do a single qubit gate, and you want accuracy that is a fidelity that is 90%. So an experimentalist can easily do that. You will not even need to put the qubit at 10 millikelvin very cold. You could probably put that at a bit higher temperature, and you will not need to do error correction because reaching 90% of fidelity for a physical gate, it is easy for an experimentalist. Now imagine that you want to do this same gate, but 1 billion times in sequence, and you want the full sequence to be 90% accurate. So if you want to do this, then each gate should be super reliable because you want a sequence of 1 billion of gates that reach 90% fidelity. So each gate should be much more reliable than this 90% fidelity. So you will need to cool a lot of qubits. You will need to do a lot of error correction. So the energy per operation you will do will grow with the duration of the algorithm. So again, this is the same thing I said before, but in different terms. So it means that you cannot reason as, okay, I count the number of operations, I multiply by some constant, which is the energy per operation. The energy per operation in an energy efficient computer depends on the algorithm you want to do. So how to do it, how to compare? Well, this is not a problem in itself. It just means that we need to optimize we need to ask to solve the full problem. We optimize with the thing I showed before. The energy per operation will depend on the algorithm, but why not? After all, this is not a problem. And we can compare the energy consumed by the classical and the quantum computer. So we did this to break RSA for various key size. So for the classical algorithm, we did a simple extrapolation from GNF. So it's called general number field sieve. It's the best classical algorithm able to break RSA. Of course, it has an exponential complexity. So if the key size is too big, the classical computer cannot do it. But it has been broken for this key size. So to remind, the key size today is 2000. And so here, this 830 is reachable by classical computer. It takes a lot of time, but they can do it. So it has been broken by a team at INRIA. And by looking at what they did, we can extrapolate the time and energy it will cost to break RSA for other key sizes based on their analysis. So it's just a simple extrapolation that we did. Here on the quantum side, we use Shor's algorithm and we can compare. And so this is what this curve represents. So the upper curve is the time in seconds that the classical computer will take to break this key size for RSA. So RSA 2000 we do not even see on the graph. It's here. So RSA 2000 again is the size we will need for current encryption device. You see that the time it takes the classical computer grows, basically it grows exponentially with the key size. And with a quantum computer, it's much more slow, the growth. And just focus on the light green curve. I won't comment all the curve, it's not very important, but focus on the light green curve. Each color basically corresponds to a different parameter we use in the model. But focus on the light green. And so when this light green is below the black one, basically it just means the quantum computer is faster. And when it's higher, it means the quantum computer is slower. So here we can compare the time. Below, we can compare the energy to solve the task. So how is this encoded? So we define energy efficiency. So it's not very important to know what it is exactly. Just basically, if a color curve is higher than the black one, it means the quantum computer spends less energy. So here, the quantum computer spends less energy than the classical one. Here, it spends more energy. And with this light green curve, we can identify a regime where the quantum computer is slower than the classical one, but spend less energy to do the task. So, of course, we could always put parameters so that this occurs. So what there is behind this parameter is very important. So here, the main thing that changed with the other parameter, so it's still very good qubit, okay, between 2 or 3 orders of magnitude better than the state-of-the-art fidelity we have. So if we wanted to do gates, and so this is the same as before. What mainly changed is that there are different ways to put electronics in a quantum computer, There are classical electronics and another thing that is called single flux quantum. It's superconducting circuits that are able to do electronics. So this community think that they could have a reduction of consumption compared to CMOS that is 10,000 times more energy efficient. So we just put this number in the simulation and we look what we get. So this is what this curve means. So of course, it is based on the idealistic parameters, but all the parameters we use are motivated by papers. We do not just put a parameter arbitrarily close to 0. We try to, while being optimistic, to still use data from scientific papers. And so here we see that, so yeah, the quantum computer is slower than the classical one, but spend less energy to do the task. So it's completely different from the computational advantage. And one thing that I would also like to say is that, yes, there are optimistic assumptions on some parameter, but we use thin code, which is very pessimistic because here we have 1 billion of physical qubits. This is absolutely huge when we observe that. Shor's algorithm to crack RSA with a surface code with a prediction of reasonable fidelity we could achieve requires 20 million qubits. So this is also something that I think is interesting. But again, this is not a proof that we will be able to have an energy advantage. It's just that we can study this question, and that's interesting to do this kind of curve. Yeah, so I'm almost done. There are 2 last things I will discuss. So the first one is how much energy and power can we save with this? Because if there is an optimization, what does it bring? So sometimes you do not save much. I mean, I talk in the context of the model I presented, okay? Because of course, this is how much you would save will heavily depend on the model. So in our model, sometimes you do not save much, but sometimes you can save really, really a lot. There are examples where by doing some non-trivial optimization, the power consumption of the computer could go from 10 gigawatt to a few megawatts thanks to the optimization by having some smart tuning of the temperature of the qubits, the signal generation, etc. So it's for a different set of regime than the one I showed before. But this is, again, something which is motivated by paper. So one important thing that changed in this example is that we did not use anymore Carnot efficiency, but an efficiency that is used in most of cryogenics today, which scale as 1 over t squared rather than 1 over t. And so this also shows that if you do not have Carnot efficiency, things can get worse much more quickly, and it becomes so much important to optimize the qubit temperature in that case. Also, do the optimization give things you could guess? So their example, it's impossible to guess. I will give you, I mean, quantitatively. There are cases where it's better to do more error correction than what a naive estimate will tell you. So to use more physical qubit for logical qubit. So your computer is bigger, but you save energy by doing this. Why? Because it allows your temperature to be higher. So you have a bigger computer, but that is more energy efficient. So it's an example that shows that reasoning with a number of physical qubits, even for a given error correction code, it's more physical qubit can be more helpful because you increase the temperature of your qubit, for instance. And so, yeah, this you cannot understand that if you do not have a holistic model of the computer, because you need to connect error correction, physics of the qubit, and cryogenics to see this kind of effect. And finally, the last point before I conclude. So what could be interesting also is that this kind of framework can also be used outside of making computer energy efficient to help designing kind of roadmaps. Because so here I will give an example. So imagine that's a constraint. You want your computer to spend no more than 10 megawatts. And people from the experimental side are probably able to improve the quality of the qubit in a manner. People from classical electronics are probably able to improve the quality of the electronics in another manner. And you would like to see which strategy is the easier to do to make the large-scale quantum computer. So here, this is the power consumption as a function of the lifetime of the qubit to crack RSA with not the kernel efficiency, but this other efficiency. What you can, so the green curve is the SFQ, so the very good electronics, and the red curve is the CMOS electronics. So the red curve consumes much more power. So for instance, you say, I want to spend 10 megawatts, and here you see you have two choices. Either you use the good electronic and a bad qubit quality, either you have a better qubit quality and you can use the bad electronic. It will give you the same power consumption. So you can trade the quality of your qubits for the performance of other aspects in the computer. And knowing this can be very useful to maximize the scalability potential of the computer, to make the best choice in the design. Okay, so that's it. So yeah, so this is really the core of the work, the philosophy of the approach. Making holistic model can be very interesting to minimize the energy consumption, the resource consumption in general, and it allows a multidisciplinary team to really work together with concrete goal and to make good decision in the design in some sense. There are clear illustration of interdependencies. Having more physical qubit per logical qubit can be more energy efficient because you can put your qubit at higher temperature. And the computational and energy advantage are different concepts. We could totally have an energy advantage without a quantum computer that is significantly faster. I'm not saying we will, I'm saying it's possible, but it requires work. And this could be easier to achieve than the computational advantage because we will not necessarily need this huge quantum computer. We could make intermediate scale quantum computer for that. Yes, this I already said. So to summarize, what I presented today is based on this paper. So there is a preliminary, so it has a different name than the name of the talk. There is a preliminary work related to that. That is this one is, that was okay, this is much more simple model behind this one, but it's to see the consequence of a limited resource on the threshold theorem. So there are some connection. And yeah, and there is a new IEEE working group that aims to propose international standard on energy efficient quantum computation and simulation. And so this work, but also other work are discussed in the working group to see how we could use that to make international standards on the matter. So feel free to join. And yeah, so I already introduced everyone here at the beginning. So all the people that participated to that work. I would also like to thank everyone here, in particular Olivier Drati, who helped us a lot to make a more realistic model by discussing with people and things like that. So this is the name of the work. And so I'm working at the University of Warsaw, and I will be a Marie Curie Fellow in the same lab in September. So for 2 more years. So yeah, thank you for your attention.
Thank you. I'm clapping for everyone. You can also clap with your reactions. So thank you a lot, Marco, for this first seminar. Now we will open a small question session. If you have questions, you can either put your camera and your mic, or if you're shy, only the mic, or if you're very shy, you can type them in the chat and I will ask them myself. And I will start by, I guess, a broad question, which is, after doing this work, I know that you said it's hard to know, and we only have holistic model for now, but do you think, like, what's your opinion on this energy advantage? Do you think that it will be possible to get the energy advantage before the time advantage or the complexity advantage?
So yeah, in my opinion, clearly, because there are many things that can be optimized. So for instance, experimentalists today work with a very bad cryogenic. It's very far from kernel efficiency. So this is this can give a huge reduction in the consumption just by asking cryogenics to make a good cryogenics. The other thing I would like to say is that so of course I made optimistic assumption in the quality of the qubit, but I would like to say that in this example, we have more than 10 billion physical qubits. when there is this consumption. So of course, as I say, it's not just a matter of proportionality with the number of qubits, but knowing that with other error correction code, we can use 20 million qubits, there is more than 3 orders of magnitude of difference. These 2 megawatts will become kilowatts in the kilowatt regime. So of course, this is complicated because when you work, for instance, with other code like surface code, you have this decoding problem. I don't know how much energy it will consume, but if it doesn't consume a hell of energy, clearly there is a big room to make quantum computer energy efficient, especially that here, when I say 10 billion of qubits, I'm asking to crack RSA 2000, which a classical computer will take billions of years. If you ask a problem that a classical computer will take, I don't know, a week, you will even need less qubit than that. So yeah.
Yeah, nice. So I guess here, so it's very nice to see like how in this interdisciplinary work merge together to make this work. But so here the main, the most costly in energy, the most costly part is the cryogenics, right? It's not the control electronics
So that's yeah, that's an interesting question. Actually, it really depends because so there are different plots I showed. When we use Carnot efficiency, it helped a little bit to change the qubit temperature, but we realized that most of the energy required was actually at room temperature in many of the points. So the cryogenics was not the dominant source. It was just generating the signals. Now, of course, I cannot make a general claim with that because it heavily depends on how you drive your qubits. So in this model, we only use a microwave driving for the qubit. So basically, it can be very energy efficient. We send a pulse, a microwave pulse, it interacts with the qubit. And if you have, for instance, if you need to tune the frequency of your qubit, you might need to inject magnetic field and dissipate much more heat on the quantum core. And then my conclusion could change. But for me, it's not obvious that the cryogenics will dominate, even in a superconducting qubit quantum computer. That's something to check.
Okay. So if anyone wants to talk. People are too shy.
Thanks for the talk. It was really interesting. I was just wondering, have you considered any applications of mitigation or other strategies for error reduction, or just the error correction?
Yeah, thanks for the question. So we only did error correction. So there is no error mitigation strategy. Yeah, there is no error mitigation strategy done here. Yeah, so that's my answer.
Thanks.
Right. No one else wants to say something? You have good comments in the chat. So before we stop the recording, I'm just saying that this was the first seminar of hopefully a series of seminars. So please stay tuned.